the next video in linear models. This is video 1 on random vectors and matrices. It corresponds to chapter 1, section 1 of the textbook. So to get started, let's just start introducing the notion of vectors and matrices where the components are no longer real numbers or even complex numbers, but instead they are random variables. So let's suppose that we have these n random variables. We'll call them y1 through yn. We will suppose that each, like the ith random variable has mean equal to mu sub I. So we're just kind of setting up some notation here. And we'll say that the covariance between yi and yj is sigma sub ij. Again, just notation. And here is where we bring up packaging all of these n random variables into a vector. So we're going to call it capital Y. I like to put my vectors always with an arrow on top of them. So while the textbook just calls this capital Y, I'm going to choose to call it capital Y with an arrow on top. And I'll try to consistently denote vectors with an arrow on top. I just find that to be helpful when you're processing what you're looking at, when you see these, like all these various symbols. It's nice to have a reminder of which things are vectors. Now, if we talk about the expected value of this vector of random variables, well, what that means is the very reasonable vector of expected values, right? So we're basically just kind of saying that the expected value of this whole vector is the vector where we take each individual expected value, right? So it is the vector of mu1 through mu n, right? And it may be worth emphasizing that this vector is a vector of real numbers, right? So while this is a vector of random variables, this is a vector of real numbers. This extends naturally to any matrix. So if we have a matrix W where the coordinates are all random variables, here I'm just saying that the coordinates are little wi sub ij, meaning that row I and column j has this particular random variable. And I'm not even bothering to tell you the dimensions of the matrix just because, right, like, I mean, you know, it's not that necessary right now. The book gives, like, you know, the full gory details, but for the purposes of just stating this, I don't think I need to be quite so explicit right now. I'll do that when it gets important. But if we take the expected value of this matrix of random variables, then again, we just kind of populate the entire matrix with each corresponding expected value of each individual random variable. And with these definitions in place, we can now talk about the covariance of a whole bunch of random variables. Presumably, you've seen the covariance of some 2 random variables in an earlier course in mathematical statistics. Well, here, if you have n random variables, then the covariance of that vector of n random variables is this familiar expression. It is the expected value of the, you know, like the random variable minus its mean times. Now, you know, usually what we put over here, right, if you're trying to sort of line this up with what you've seen before in mathematical statistics, you'd think the other random variable goes here, right? It's that random variable minus its mean. Well, if you, but what we're actually writing here is the same random variable all over again, but transpose, right? So this is the difference of some 2 vectors. If we take its transpose, then we go from a column vector to a row vector. So that's what we're doing here. And then we are taking the matrix product with this column vector. So what you get is a column vector times a row vector, and that gets you a whole matrix, right? So you know, brush up on the linear algebra necessary for this if you need it, but you know, check the dimensions. You're going to get an n by n matrix, and what you can check, you know, referring back to your familiar definition of just the covariance of some two random variables, you can check each coordinate, right? If you look at sigma 1, 1, and you think about like, this row vector where the first one is going to, right, like the first component is basically going to be y1 minus mu1, and then you're going to be multiplying that times the first column of this vector, which is again going to be y1 minus mu1, and this expected value is what's going to go here in this coordinate. But that is nothing other than your training in mathematical statistics. This is the same thing as the variance of y1, which we agreed we were going to denote by sigma 1, 1. And if you did it with the next coordinate, like let's just talk about this sigma 1, 2. Well, if you work out all your linear algebra, you'll see that this coordinate comes from taking the expected value of y1 minus mu1 times the y2 minus mu2. So, right, this comes from taking the first row of this matrix, which is y1 minus mu1, and the second column of this matrix, which is y2 minus mu2. So you get these two, and we're taking their expected value. Well, this is nothing other than, right, again, recalling your training in mathematical statistics, this is the same thing as the covariance between y1 and y2, which we agreed to call sigma 1, 2. So that's what you get here in this coordinate, and you can kind of see that if you continue filling in the rest of the matrix, that you get all of these sigma indices throughout the matrix. Now, let's define that a matrix Y is called singular. I guess I should maybe highlight like where we are defining certain things. So like here, I am defining that, I am defining that. These are definitions. And so next we're going to define what it means for a vector of random variables to be singular, and it is singular if its covariance matrix is singular. Notice that the covariance matrix is a matrix of real numbers, right? Each one of those sigma sub ij's, those are real numbers, and so so when we talk about whether the matrix is singular or not, we're referring to our linear algebra idea of just like a matrix is singular if and only if it is non-invertible or not invertible. And that happens if and only if the determinant is equal to 0, because this is a square matrix, and so on and so on. It is worth knowing the distributive properties for expectation on these vectors. So if A is a constant, right, a matrix of just plain real numbers, or possibly variables, but whatever, let's just say constant numbers. And if Y is a vector of random variables and B is a vector of constant numbers, then the expectation distributes in, right? And since B is constant, then the expectation of a constant is just equal to that constant. And, but also importantly, right, a matrix, right, even multiplying by an entire matrix, it's still just treated like a constant and it moves outside of the expectation. So expectation has this like very strong linear property, which should be familiar from the linearity of expectation in mathematical statistics, but just here now applied to vectors. Covariance will look a little bit familiar, but this one is a bit of a stretch from what's familiar from mathematical statistics. You know, like with mathematical statistics, we tend to think like the covariance of, some two random variables satisfies this or that property. And so, this time because the multiple variables, random variables, are all packed into this vector y, then it's not going to look quite like it did when we used to talk about covariance for just two variables at a time. But anyway, what it turns out is that we can say that the covariance of this constant is just 0, right? Like as a vector of all constants, we're kind of familiar with the fact that the covariance of some two constant random variables is always 0, and so that makes it hopefully not surprising why when you take the covariance of this thing, that b just kind of turns into 0 and doesn't show up in the final formulation. So I think that makes sense. It's perhaps a little bit more surprising that the matrix A kind of pops out like we're somewhat used to, like the variance or the standard deviation popping out when, like you take a random variable and multiply by a constant, like that's kind of familiar from mathematical statistics. But that's not all that happens here with covariance, because then you also have specifically on the right-hand side the transpose of A as well. And you can kind of think about this as like there's this formula for the covariance that you get. You think about like the variance, for example, and if it were multiplied by a constant number, then we typically show you that that constant can move outside of the variance, but it becomes squared. That's kind of like what's happening here, but it turns out that, that because you have something that's kind of like A and kind of like A, and if you could put them together, it would be like the square matrix, but it's it doesn't quite perfectly line up in like the simple way that you might hope that it does, because the transpose really has to like stay on one side. You can't flip these matrices around. Hopefully it's familiar that you can't just swap two matrices around, because matrix multiplication is not commutative. So anyway, so this may be a bit more of a surprising result, but we're about to prove something. But basically we're about to prove it. I mean, in fact, we're about to prove something that is more general than this, but this will be a consequence of what we're about to do. Now, because the covariance has this formulation as, matrix something and then matrix transpose, now this is something that not everybody, right? Like not everybody learns about non-negative definite matrices in linear algebra. So if you have, then hopefully you kind of recognize that having that form makes this a non-negative definite matrix. If that was not in your background in your previous linear algebra course, then you can take it on faith. I think it's also explained in the appendix of the textbook, or I am also doing a video series on abstract linear algebra. And so I will, at some point, get around to talking about that. I think that actually comes up pretty late in the linear algebra class. So you can consult that if that's a useful reference, but if not, maybe check the appendix or just do some searching, right? One way or another, come to terms with the fact that this explanation of the covariance matrix being always a non-negative definite matrix. And a fact about non-negative definite matrices is that they are non-singular if and only if they are positive definite. Again, whole idea of positive definite, very similar to non-negative definite. And if you need, to consult a reference on what all of that means, then again, right, like there's the appendix, there's my other video series, or you can just do some Googling or something. But let's end this on an exercise, right? The very exercise that I was promising would derive that earlier equation. So we are going to let W be an R by S matrix of random variables. So this is just some notation, right? You may or may not have seen this notation where I write the symbol with a superscript R cross S, so that's just notation telling you the dimensions of this matrix. So I do likewise call this matrix A an n by R matrix of constant real numbers, and we have this matrix C, which has dimensions n by S. Also a matrix of constants. It should hopefully be readily sort of clear that we're going to multiply A times W because the dimensions there match for matrix multiplication. and the resulting matrix will be an n by s matrix. Well, then that makes sense that we would have write this matrix C having dimension n by s. It's getting added to this n by s matrix. Okay, the claim is that the expected value under these assumptions for AW plus C is kind of exactly what you would expect, right? You get this linear distribution where it kind of grounds out in taking the expected value of the random part. Moreover, we're going to show that if B is a constant matrix then of the appropriate dimension, then when you take the expected value yet again, right? Like even if you have a matrix that is on the right-hand side, still the expected value kind of distributes only to the random part. Moreover, at the very end, we're going to prove that part that I talked about before, that if the dimension S is 1, which is to say we're talking about having the dimension of S is 1, then what we're talking about here is that S over there is 1, which tells us that the matrix W is a column vector, and therefore this is kind of confirming what we were talking about earlier in the video. So okay, let's get into the proof. So we are going to take the expected value of AW plus C, and we're going to try to prove that it's equal to some other matrix. Well, the sort of natural way to show that some two matrices are equal is to show that they are equal coordinate by coordinate, right? That each coordinate of the first matrix, right, the ij coordinate of this first matrix is equal to the ij coordinate of the other matrix that we are claiming it equals. So that's why we have this ij coordinate, right? So we're going to look at the ij coordinate, right, an arbitrary coordinate of this matrix, and prove that it's equal to the same coordinate in the other matrix. That way the two matrices are coordinate by coordinate equal, so they must be the same matrix. Okay. First move that I can make here is say that, well, just by definition of the expected value of a matrix of random variables is right, so this matrix of expected values is equal to the expected value of the matrix, and in particular that is true still when fixing the ij coordinate, right? So the ij coordinate of this matrix equals the expected value of the ij coordinate of this matrix, right? Fairly trivial move, although, often when you when you're just starting to learn this stuff, I hope it is helpful that I somewhat over-explain it, but okay, so that's our first move. Fairly trivial move. Okay, but now we are talking about the ij coordinate of a matrix, and it will be sort of useful to say, to use the formula for the ij coordinate of a product, right? So because this is matrix A times matrix W, then it has this, I believe we sometimes call it like the Cauchy product or the convolution formula or something like that. But in any case, this is the formula for the matrix product at coordinate ij. So this is what you get at the ij coordinate of AW. Of course, here we're just getting the ij coordinate of matrix C. The point of doing that is because I know that I can distribute into that the expectation, right? This is just the linearity of expectation for a sum of random variables, basically, right? That you can distribute it into plus, and also constant multiples pop out, basically. And in some sense, this is the moment at which I've kind of like distributed E all the way in, like as far in to these coordinates as I possibly can. Because I have that, I was like able to use linearity. Now I kind of want to start moving backwards, right? I want to start like now going back to, so anyway, so what I'm saying is that if this is the expected value of random variable W sub kj, then that is the same thing as the coordinate kj in the matrix of the expected value of W, right? Again, kind of coming, it's this trivial move that I'm somewhat over-explaining because we're just getting used to this stuff. But this idea that like the expected value of a matrix of random variables is equal to the matrix of expected values, right? So it's that interchange that I'm doing in this move here. And then, again, just by definition of like, the ij coordinate of a matrix product and taking matrix sums and so on, that we get back to this equation. And this is what we were trying to prove is equal to the starting thing, right? So what we had set out to do all along, we have now finished. And so there you go, right? That's the proof, right? That's the proof of this equation right here. Next, we have to come back and talk about proving the distribution of expectation for, right, like when you have a matrix on the right-hand side. I'm not going to bother doing that because the proof is so similar to what we just did, so I'm leaving that as an exercise to the viewer. But I will now start talking about this covariance of AW plus C, which right up here, we see the claim that when S is equal to 1, right, so that means that W is a column vector, then we get this equation. So let's see what we can do here. Now, as a matter of notation, I want to write the expected value of AW plus C as just plain mu, right? So that's just so much less writing. And so just to have like a nice clean symbol for me to write and for you to read, let's adopt that notation. And somewhat similarly, though, I would also like to call the expected value of W alone, I want to call that mu sub W, right? So again, just for cleanliness of reading, I'm going to use this notation. Now, to make our first move, by definition, the covariance of any matrix is that matrix minus its expected value, which we agreed we would call mu, and then multiply by the transpose of the same thing. So that's what we have here. This is just by definition of the covariance. Now from here, I'm going to try to strategically distribute, and the motivation for sort of how I'm strategically distributing is, well, I just tend to think that like these, AW plus C, that should kind of get grouped together. So I'm gonna kind of like group AW plus C and AW plus C over here as well. Notice that the transpose, right? Because over here we're taking the transpose, so the transpose kind of distributes in. So if we didn't want to have it on the outside, we would distribute it to the inside. You'd get mu prime there. You'd get C prime here. Now you have to be careful because here you would not get A prime W prime. You have to remember your linear algebra that if you take the transpose of a product, you get the individual transposes, but they are written in reverse order. But anyways, that's actually, I guess that I'm not using that in this next step anyway, so I might as that'll be important in the step after. But for right now, just know that I'm grouping AW plus C and I'm taking the transpose, right? So that's how I get this AW plus C transpose over here. I'm like distributing this to that. And again, don't worry about this. I'm not doing this just yet. But anyway, so that's how I get this first term here, right? This first term comes from just grouping things that way and then distributing. The next thing I do is I distribute it over here. So that's how I get minus AW plus C all times mu prime, because the prime distributed to that mu in that particular factor there. Okay, then I continue with my distribution. So I'm going to take my minus mu and distribute it here. So that's where I get minus mu times AW plus C prime, because again, right, the prime that was out here distributed in, and I'm kind of just like sending it over to this term here. So anyway, that's where that comes from. And then next we take minus mu times minus mu prime. So that's why we get a plus, and we get mu prime. In the next step, I can start to distribute the expected value based on everything that we've already said, right? So we know that the expected value distributes over these matrix sums. And so what I'm going to start doing here is this is all the result of just this multiplication and distribution, right? So in this step here, I'm taking this prime here, I'm distributing it so that like it's no longer on the outside, it's now that prime is on this C, and we can't write it as AW, we have to write it as W prime A prime, and now I'm doing the distribution, so I'm gonna get this AW here, distributing to the W prime A prime there. That's where I get this term. Okay. Then if I do the next distribution, I get AW times C prime, which is right here. Next, I do C times W prime A prime. So that goes here, and then C times C prime is next. So that explains all of these terms. Then keep in mind that I'm, right, like where does this term come from? Well, it comes from here, and it comes from the fact that the minus is constant. So the expectation just moves over the minus, right? So I can ignore that minus. That's why this minus is here. And then I'm taking the expected value of this AW plus C prime. Well, what is the expected value of AW plus C prime? Well, it's going to just be mu prime, right? Mu prime, right, like the expected value of AW plus C, that's mu, and it's got a prime on it. I'm kind of taking it for granted that the expectation distributes into the transpose, but that's easy enough to prove if you want to prove that, but I take that to be a step that is straightforward enough to prove that I'm not going to spend time on it. So anyway, so that's where that mu prime comes from, is taking AW plus C prime and pushing the expected value to it. And so so that gets me this minus mu prime. Oh, sorry, and I just explained that in reference to this right here. But I also have, I have another term here, right? So I have this one here, and kind of the same story there, right? Because it's got a minus, right? That's a minus. This is all just going to turn into mu, and this stays mu prime. So we also get a minus mu prime here as well, right? So we get a minus mu prime here. We get another one here. And so that's why I have two of them. So that explains the two. I hope that's clear. Finally, we get this mu prime. We're taking its expected value because remember, this is all distributing in the expected value. But because that is a constant, then the expected value of mu prime is just equal to mu prime. So we just leave it alone. Okay, so there's that move. Next, we move on to the next step. And here we know that since A and A prime are both constants, right, we can just move the expected value past the A and the A prime. The middle here is WW prime. Those are all random variables, so the expected value kind of just distributes into the random part. That's what I'm doing here. By the way, be careful. EWW prime does not equal mu W prime, right? You might think that it does, right? That you could distribute the expectation to each one of these individually. But remember that for one thing, we haven't proved that, so you can't sort of do that move because we haven't proved that it's valid. In fact, it's not valid. That will get you the wrong answer in many, in almost every case. And that is because distributing the expectation into a product, and here I'm kind of just, again, sort of like leveraging your memory of mathematical statistics. The expectation of a product only distributes when the two random variables are independent, right? So for distribution into a sum, independence does not matter, but distribution into a product only works when the random variables are independent. Well, W and W prime are made up of the same random variables, slightly reorganized by the transpose, but these two random variables well, they're not two random variables, these two matrices of random variables, in no sense are independent. And so not only have we not proved that you can't do that distribution here, because they lack anything like independence, then it's certainly a wrong move to distribute into this product. Okay, anyway, getting back to our work here, that's why when I distribute the expectation, I have to stop at EWW prime. But let's look at all the rest, right? Like when I distribute here, right? A and C prime are both constants, and so I can distribute the expectation into just the W, and that's why it turns into this mu sub W, because we agreed that we were going to call the expected value of W just mu sub W. This is going to just turn into mu W prime. This is nothing but a constant, so it just stays constant like that. If we take these two terms, I mean, this is minus 2 mu mu prime plus mu mu prime, so that's just a single, right? It's just minus, so that's why I have a minus here. It's minus mu mu prime, right? Because I have negative 2 of them and then positive 1 of them, so I just have negative 1 of them. And then writing out what mu mu prime is, right? I'm just using the fact that mu mu prime is in fact equal to a mu sub W plus C, and then mu W prime, A prime plus C prime, right? And this is because, right, if you're taking the expected value of AW plus C, well, you could just distribute the expected value into that. And so, right, so this all along, right, this was always equal to A mu W plus C, right? And then, again, the same kind of story happens with the transpose, but remember that when it comes to a product, you have to write them in reverse order when you take the transpose. So anyway, that's how I get this term here. It comes from having just a single minus mu mu prime. I know this has been long, this has been very talky, we're almost done. So what can we do from here? Well, if we take this and distribute it out, you'll see that lots of things cancel. After all, you're going to get an A mu W times mu W prime A prime. Now that part actually doesn't cancel, so that one kind of survives. Where does it go? Like, where does it show up? Well, you know, that basically is going to amount to A mu W prime A prime. So that's that term from distributing this over to here. But it's, you know, right, you don't see it in the next line. Why? Because I'm taking this term and putting them together, right? They both have the matrix A on the left, so I'm going to move that matrix A outside of both of them, right? Basically factoring out that matrix. And so what's left over is the EWW prime from that term, and the mu W prime from that term, with the A factored out on the left, and of course also with the A prime factored out on the right. So that's where that term went. Okay, so next let's distribute A mu W, and there's a minus because there's a minus here. Anyway, so let's now take A mu W and distribute it to C prime. Well, what happens there? You've got an A mu W C prime. You have a minus AW C prime, mu W C prime. You also have a plus of exactly the same thing right here, and so they cancel. Okay, then we do minus C mu W prime A prime. Well, you also have a plus up here, and they cancel. You also get C distributed to C prime, but it's a minus. You also have a plus here, so they cancel. And so in fact, this is the only thing left over after all those other things cancel. Now, if you look at this, oh, and I think I have a typo here, I should have written it, let me just rewrite it entirely, A cove of W A prime. So my claim here is that the covariance of W is in fact the same thing as expected value WW prime minus mu W prime. And this, right, this is like, very familiar, right? This is like a familiar formula. You'd recognize it from mathematical statistics. The parallel formula there is that the variance of x is equal to the expected value of x squared minus expected value of x squared, like that. So this, right, the identification of the covariance of just W with this very parallel looking formula, proving that those two things are the same thing is rather straightforward. And so I'll do it by request. If you want to see me prove the equality of those two components, I'll do it in kind of like a supplementary video if anybody asks for it. But I think hopefully you can handle it on your own. But if it's harder than, I haven't even done it in a long time, so I don't even really remember how hard it is. So if it turns out to be pretty hard, then leave a comment, make a request, and I can make like a supplementary video that I'll add into the playlist. But at least for now, I'm just going to take that for granted, and that means that the proof is complete. And that might have seemed like a lot, but then again, this subject is a lot. So end of video, and I'll see you in the next.